Welcome to this course on ETL and data pipelines with Shell, Airflow, and Kafka. This course is ideal for aspiring big data engineers, machine learning engineers, data warehousing specialists, as well as developers. In this course, you will master various ETL and data pipeline tools and techniques. You will utilize bash scripts as well as cutting-edge open source tools such as Apache Airflow and Apache Kafka to build data pipelines for processing and moving data between various systems in a data platform. You will practice what you learn through hands-on labs in each module, as well as demonstrate your newly acquired skills in a real-world inspired final project. This course has 4 instructors: Yan Lo, Jeff Grossman, Sabrina Spillner, and Ramesh Sanareddy. Yan Lo, PhD, is a data scientist and developer at IBM Canada. He has been building innovative AI and cognitive applications in various areas, such as mining software repositories, personalized health management, wireless networks, and digital banking. Yan received his PhD in machine learning from the University of Western Ontario. Jeff Grossman, PhD, has a background in pure mathematics, geophysical signal and image processing, medical imaging, and data science and engineering. He is a founder of 617 Data Solutions, Inc. and serves as a subject matter expert at SkillUp Technologies, developing data-related educational content, and volunteers with Camdia Digital Forum as Associate Member, Alberta, Canada. Sabrina Spillner is a senior instructional designer and content developer with SkillUp Technologies. She specializes in learning solutions across sectors. For the past 18 years, Sabrina has been a pathfinder, adopting new approaches and technologies to create innovative learning solutions. She has worked with Orbis Software, the EU, the University of Cambridge, KPMG UK, and KPMG Lower Gulf. And Ramesh Sanareddy holds a bachelor's degree in information systems from the Birla Institute of Technology, Pilani. He has 2.5 decades of experience in information technology infrastructure management, database administration, information integration, and automation. He worked for companies such as Integraph, Genpact, HCL, and Microsoft. Currently, he is a freelancer and pursues his passion for teaching. He teaches data science, machine learning, programming, and databases. In this course, you will explore the fundamental principles and techniques behind ETL and ELT processes. In Module 1, Data Processing Techniques, you will learn to describe what an ETL pipeline is, describe why ELT is an emergent trend, describe the trending shift from ETL to ELT, list examples of raw data sources, name data loading techniques, and differentiate batch loading from stream loading. You will also explore how to construct a basic ETL data pipeline from scratch using bash shell scripting and explore use cases for the 2 main paradigms within data pipeline engineering: batch and streaming data pipelines. In Module 2, ETL and Data Pipelines Tools and Techniques, you will learn to describe how shell scripting can be used to implement an ETL pipeline, describe what a data pipeline is, describe data pipeline solutions for mitigating data flow bottlenecks, differentiate between batch and streaming data pipelines, and discuss data pipeline technologies. You will also further cement this knowledge by exploring and applying a popular open-source data pipeline tool named Kafka. In Module 3, Building Data Pipelines Using Airflow, you will learn to list the main principles of Apache Airflow, interpret Airflow pipelines as Python scripts that define Airflow DAG objects, list key advantages of defining workflows as code, identify current DAGs in your environment and set up dependencies amongst tasks, and use logging capabilities to monitor the task status and diagnose problems with DAG runs. In Module 4, Building Streaming Pipelines Using Kafka, you will learn to list the main components of an ESP, recognize Apache Kafka as an event streaming platform, describe an end-to-end event streaming pipeline example, and describe what the Kafka Streams API is. And finally, you can test your hands-on knowledge in Module 5, Final Project. Your assignments will be to complete a project to create an ETL pipeline using an Airflow DAG and build a streaming ETL pipeline using Kafka. To get the most from this course, watch every video and check your learning by taking all quizzes. Use the discussion forums to connect with your peers and the teaching assistants. And most importantly, make sure you complete the hands-on labs to practice your new skills and demonstrate your abilities. Congratulations on beginning the next step on this exciting journey, and good luck! Welcome to ETL Fundamentals. After watching this video, you will be able to describe what an ETL process is, describe what data extraction means, describe what data transformation means, describe what data loading means, and list use cases for ETL processes. What is an ETL process? ETL stands for Extract, Transform, and Load. ETL is an automated data pipeline engineering methodology whereby data is acquired and prepared for subsequent use in an analytics environment, such as a data warehouse or data mart. ETL refers to the process of curating data from multiple sources, conforming it to a unified data format or structure, and then loading the transformed data into its new environment. The extraction process obtains or reads the data from one or more sources. The transformation process wrangles the data into a format that is suitable for its destination and its intended use. The final loading process takes the transformed data and loads it into its new environment, ready for visualization, exploration, further transformation, and modeling. The curated data may also be utilized to support automation and decision-making. What is extraction? To extract data is to configure access to it and read it into an application. Normally, this is an automated process. Some common methods include web scraping, where data is extracted from web pages using applications such as Python or R to parse the underlying HTML code, and using APIs to programmatically connect to data and query it. The source data may be relatively static, such as a data archive, in which case the extraction step would be a stage within a batch process. On the other hand, the data could be streaming live and from many locations. Examples include weather station data, social networking feeds, and IoT devices. What is data transformation? Data transformation, also known as data wrangling, means processing data to make it conform to the requirements of both the target system and the intended use case for the curated data. Transformation can include any of the following kinds of processes: cleaning, fixing errors or missing values; filtering, selecting only what is needed; joining disparate data sources, merging related data; feature engineering, such as creating KPIs for dashboards or machine learning; and formatting and data typing, making the data compatible with its destination. What is data loading? Generally, this just means writing data to some new destination environment. Typical destinations include databases, data warehouses, and data marts. The key goal of data loading is to make the data readily available for ingestion by analytics applications so that end users can gain value from it. Applications include dashboards, reports, and advanced analytics such as forecasting and classification. There are many use cases for ETL pipelines. A very large amount of information is either already recorded or being generated but is not yet captured or accessible as a digital file. Examples include paper documents, photos and illustrations, and analog audio and video tapes. Digitizing analog data includes extraction by some form of scanning, analog to digital transformation, and finally, storage into a repository. Online transaction processing, or OLTP systems, do not save historical data. Accordingly, ETL processes capture the transaction history and prepare it for subsequent analysis in an online analytical processing, or OLAP system. Other use cases include engineering features, or KPIs, from data sources as preparation for ingestion by dashboards used by operations, sales and marketing, customers, and executives, and training and deploying machine learning models for prediction and augmented decision making. In this video, you learned that ETL, Extract, Transform, Load, is an acronym for an automated data pipeline engineering methodology, whereby data is acquired and prepared for subsequent use in an analytics environment, such as a data warehouse or data mart. The extraction process obtains the data from one or more sources. The transformation process wrangles the data into a format that is suitable for its destination and its intended use. The final loading process takes the transformed data and loads it into its new environment, ready for visualization, exploration, further transformation, and modeling. And finally, ETL is used for curating data and making it accessible to end users. For example, training and deploying machine learning models for prediction and augmented decision-making. Welcome to ELT Basics. After watching this video, you will be able to describe what an ELT process is, list use cases for ELT processes, and describe why ELT is an emergent trend. What is an ELT process? ELT stands for Extract, Load, and Transform. ELT is an acronym for a specific automated data pipeline engineering methodology. ELT is similar to ETL in that similar stages are involved, but the order in which they are performed is different. For ELT processes, data is acquired and directly loaded, as is, into its destination environment. From its new home, usually a sophisticated analytics platform, such as a data lake, it can be transformed on demand and however users wish. Like ETL, the first stage in the ELT process is extraction. The extraction process obtains the data from all sources and reads the data, often in an asynchronous fashion, into an application. The loading process takes the raw data as is and loads it into its new environment where modern analytics tools can then be used directly. The transformation process for ELT is much more dynamic than it is for conventional ETL. Modern analytics tools in the destination environment enable interactive, on-demand exploration and visualization of your data, including advanced analytics such as modeling and prediction. Use cases for ELT processes typically fall within the high-performance computing and big data realms. Cases include dealing with the massive swings in scale that come with implementing big data products, calculating real-time analytics on streaming big data, and bringing together data sources that are highly distributed around the globe. In terms of speed, moving data is usually more of a bottleneck than processing it, so the less you move it, the better. Therefore, ELT may be your best bet when you want flexibility in building a suite of data products from the same sources. Why is ELT emerging? Firstly, cloud computing solutions are evolving at tremendous rates due to the demands of big data. They can easily handle huge amounts of asynchronous data, which can be highly distributed around the world. Cloud computing resources are practically unlimited, and they can scale on demand. Unlike traditional on-premises hardware, you only pay for the computing resources you use. You do not have to worry about underutilizing resources, that is, overspending on equipment. With ELT, you can have a clean separation between moving data and processing data. Of course, cloud computing is equally prepared to handle the most challenging cases for either of these two tasks. There may be many reasons to transform your data and just as many ways to do it. Thus, ELT is a flexible option that enables a variety of applications from the same source of data. Because you are working with a replica of the source data, there is no information loss. Many kinds of transformations can lead to information loss, and if these happen somewhere upstream in the pipeline, it may be a long time before you can have a change request met. Worse yet, the information may be forever lost if the raw data is not stored. In this video, you learned that ELT processes are used for cases where flexibility, speed, and scalability are important. Cloud-based analytics platforms are ideally suited for handling big data and ELT processes in a cost-efficient manner. And ELT is an emerging trend mainly because cloud platform technologies are enabling it. Welcome to comparing ETL and ELT. After watching this video, you will be able to list key differences between ETL and ELT, describe ELT as an evolution of ETL, and describe the trending shift from ETL to ELT. Differences between ETL and ELT. For one thing, the transformations happen in a different order. Transformations for ETL pipelines take place within the data pipeline before the data reaches its destination, whereas transformations for ELT are decoupled from the data pipeline and happen in the destination environment at will. They also differ in flexibility in how they can be used. ETL is normally a fixed process meant to serve a very specific function, whereas ELT is flexible, making data readily available for self-serve analytics. They also differ in their ability to handle big data. ETL processes traditionally handle structured relational data, and on-premise computing resources handle the workflow. Thus, scalability can be a problem. ELT, on the other hand, handles any kind of data, structured and unstructured. And to handle scalability problems posed by big data, ELT leverages the on-demand scalability offered by cloud computing services. With regard to data discovery and time to insight, ETL pipelines take time and effort to modify, which means users must wait for the development team to implement the requested changes. ELT provides more agility. With some training in modern analytics applications, end users can easily connect to and experiment with the raw data, create their own dashboards, and run predictive models themselves. ELT is a natural evolution of ETL. One of the factors driving that evolution is the demand to release raw data to a wider user base for the enterprise. Traditionally, ETL processes include an intermediate storage facility called a staging area. This is a holding area for raw extracted data where you can run processes prior to loading the resulting transformed data into a data warehouse or a data mart. This sounds a lot like an ELT process, and the staging area fits the description of a data lake, which is a modern self-serve repository for storing and manipulating raw data. A traditional staging area, however, is not something that is usually shared across the company. It's a private, siloed area set aside for developing, monitoring, and performance tuning the data pipeline and its built-in transformations. Along with the ever-increasing ease of use and connection capabilities of analytics tools, raw data sources have become much more accessible to less technical end users. Accordingly, the paradigm is shifting to self-service data platforms. There is still a place for conventional ETL in developing data pipelines, so ETL is not disappearing anytime soon. However, there is a trend taking place, a trend which is favoring modern ELT over conventional ETL. The trend is being driven by the pain points that ELT solves, namely the lengthy time to insight, the challenges, for example, scalability imposed by big data, and the conventional siloed nature of data. In this video, you learned that key differences between ETL and ELT are the location where the transformation takes place, flexibility, big data support, and time to insight. One of the factors driving the evolution from ETL to ELT is the demand to release raw data to a wider user base for the enterprise. Conventional ETL has many applications and still has its place. And ELT is more flexible than ETL, enabling end users to perform ad hoc, self-service data analytics in real time. Welcome to Data Extraction Techniques. After watching this video, you will be able to list examples of raw data sources, describe data extraction techniques, and relate use cases with data sources and extraction techniques. Here are some examples of raw data sources: archived text and images from paper documents and PDFs, web pages including text, tables, images, and links, analog audio and video, which can be recorded on media such as magnetic tapes or streaming in real time, survey data, statistical and economic data, and transactional data from business, financial, real estate, and point-of-sale or POS transactions. And here are more examples of raw data sources: event-based data such as social media streams, weather data from weather station networks, Internet of Things or IoT sensor streams, medical records such as prescription history, medical treatments, and medical images, and also personal genetic data encoded in DNA and RNA samples. Evidently, data is everywhere, and much of it is highly sensitive and personal, and needs to be very carefully guarded for privacy and other concerns. There are many techniques for extracting data, depending on the kind of data source and the intended use of the data. Examples include optical character recognition, or OCR, which is used to interpret and digitize text scanned from paper documents so it can be stored as a computer-readable file. Analog to digital converters, or ADCs, which can digitize analog audio recordings and signals, and charge-coupled devices, or CCDs, that capture and digitize images. Opinions, questionnaires, and vital statistical data obtained through polling and census methods. And cookies, user logs, and other methods used for tracking human or system behavior. More techniques include web scraping, used to crawl web pages in search of text, images, tables, and hyperlinks, APIs, which are readily available for extracting data from all sorts of online data repositories and feeds, such as government bureaus of statistics, libraries, weather networks, online shopping, and social networks, SQL languages for querying relational databases, and NoSQL for querying document, key value, graph, or other non-structured data repositories. Edge computing devices, such as video cameras that have built-in processing that can extract features from raw data. And finally, biomedical devices, such as microfluidic arrays that can extract DNA sequences. Here are a few high-level examples of use cases, along with their raw data sources and extraction techniques. You can use APIs to extract data from multiple structured data sources for integration into a central repository. You can also use APIs to capture periodic or asynchronous events to store them in a history archive. Rather than transmitting potentially very large volumes of redundant data from IoT devices, you can use edge computing to reduce that data volume by extracting features of interest from the raw data. Often this kind of extraction at the source is impractical, so the data is migrated to storage as is for further processing, analysis, or modeling. Also, you can use medical imaging devices and biometric sensors to acquire data for diagnostic purposes. In this video, you learned that some examples of raw data sources are archived text and images from paper documents and PDFs, and web pages including text, tables, images, and links. Many extraction techniques rely on sophisticated technology to capture information from raw data. SQL, NoSQL, web scraping, and APIs are important techniques for extracting data. And you can use medical imaging devices and biometric sensors to acquire data for diagnostic purposes. Welcome to Introduction to Data Transformation Techniques. After watching this video, you will be able to name data transformation techniques, compare schema on write versus schema on read, and list ways information can be lost in transformation. Data transformation is mainly about formatting the data to suit the application. This can involve many kinds of operations, such as data typing, which involves casting data to appropriate types, such as integer, float, string, object, and category. Data structuring, which includes converting one data format to another, such as JSON, XML, or CSV to database tables. as well as anonymizing and encrypting transformations to help ensure privacy and security. Other types of transformations include cleaning operations for removing duplicate records and filling missing values, normalizing data to ensure units are comparable, for example, using a common currency, filtering, sorting, aggregating, and binning operations for accessing the right data at a suitable level of detail and in a sensible order, and joining or merging disparate data sources. Schema on write is the conventional approach used in ETL pipelines, where the data must be conformed to a defined schema prior to loading to a destination, such as a relational database. The idea is to have the data consistently structured for stability and for making subsequent queries much faster, but this comes at the cost of limiting the versatility of the data. Schema on read relates to the modern ELT approach, where the schema is applied to the raw data after reading it from the raw data storage. This approach is versatile since it can obtain multiple views of the same source data using ad hoc schemas. Users potentially have access to more data since it does not need to go through a rigorous pre-processing step. Whether intentional or accidental, there are many ways in which information can be lost in transformation. We can visualize this loss as follows. Raw data is normally much bigger than transformed data. Since data usually contains noise and redundancy, we can illustrate the information content of data as a proper subset of the data. Correspondingly, we can see that shrinking the data volume can also mean shrinking the information content. Either way, for ETL processes, any lost information may or may not be recoverable, whereas with ELT, all the original information content is left intact because the data is simply copied over as is. Examples of ways information can be lost in transformation processes include lossy data compression. For example, converting floating point values to integers, reducing bit rates on audio or video. Filtering. For example, filtering is usually a temporary selection of a subset of data, but when it is permanent, information can easily be discarded. Aggregation. For example, average yearly sales versus daily or monthly average sales. And edge computing devices. For example, false negatives in surveillance devices designed to only stream alarm signals, not the raw data. In this video, you learned that data transformation is generally about formatting data to suit the needs of the intended application. Common transformation techniques include typing, structuring, normalizing, aggregating, and cleaning. Schema on write is the conventional approach used in ETL pipelines, and schema on read relates to the modern ELT approach. And finally, ways of losing information in transformation processes include filtering, aggregation, using edge computing devices, and lossy data compression. Welcome to Data Loading Techniques. After watching this video, you will be able to list data loading techniques, differentiate batch loading from stream loading, explain push versus pull, and describe parallel loading. There are many techniques for loading data, some of which are full loading. You can load an initial history into a database, after which incremental loading is applied to insert new data or to update already loaded data. You can schedule data loading to occur on a periodic basis, or you can load it as required on demand. Data can also be loaded in batches, or it can be streaming continuously to its destination. The data can be either pushed to a server or pushed to clients by a server. And data is usually loaded serially, but it can also be loaded in parallel. Full loading refers to loading data in one large batch. This is used, for example, when organizations want to start tracking transactions in a new data warehouse, and they copy the existing transaction history from the old to the new system. Then it's a matter of incrementally loading transactions as they arise, thus ensuring the transaction history is tracked. With incremental loading, the target data store is appended to, such that only the changes are loaded. This is useful for accumulating historical data, such as transactions, weather, and browsing history. The volume, velocity, and demand for the data determine whether the data is loaded in batches or streamed live. Data loading processes can be scheduled or initiated on demand. Data is often loaded on a schedule. For example, daily point-of-sale transactions can be loaded into a database at the end of each day during off-peak hours. Loading tasks can be scheduled with tools such as Windows Task Scheduler or with cron on Unix-like systems. On-demand loading is also very common and relies on triggering mechanisms, such as when the source data reaches a specified size, when an event is detected by the source system, such as motion, sounds, or temperature changes, or when a user requests data, such as online videos, music, or web pages. Batch and stream data loading are two ends of a spectrum of loading methods. Batch loading refers to loading data in chunks defined by some time windows of data accumulated by the data source, usually on the order of hours to days. At the other end of the spectrum, we have stream loading, which loads data in real time as it becomes available. In between batch and stream loading, we have micro-batch loading. This is used when eminent processes need access to a small window of recent data. Push and pull data loading methods are based on a client-server model. A pull refers to a client initiating a request for data from a server. The server then responds to the client's request and delivers the data. Examples of pull technologies include RSS feeds and email. With push technology, the client subscribes to a service provided by a server so that the server can then push the data to the client as it becomes available. Examples include push notifications and instant messaging services. Parallel loading can be employed on multiple data streams to boost loading efficiency, particularly when the data is big or has to travel long distances. Similarly, by splitting a single file into smaller chunks, the chunks can then be loaded simultaneously. In this video, you learned that some data loading techniques are scheduled, on-demand, and incremental. Data can be loaded in batches, or it can be streamed continuously into its destination. Servers can push data to subscribers as it becomes available. Clients can initiate pull requests for data from servers. And you can employ parallel loading to boost loading efficiency of large volumes of data. Welcome to ETL using shell scripting. After watching this video, you will be able to describe how shell scripting can be used to implement an ETL pipeline and explain how ETL scripts or tasks can be scheduled. Imagine a scenario that you have been tasked with, reporting the hourly average, minimum, and maximum temperatures from a remote sensor that supplies the temperature on demand and feeding the results to a dashboard every minute. You are given APIs that read the temperature and print it to standard output, and load the stats to a repository which is available to a reporting tool such as a dashboard. Here is an outline of how this can be achieved using bash scripting. Let's sketch the workflow for your ETL pipeline, starting with the weather station and its data interface. The extraction step involves obtaining a current temperature reading from the sensor using the supplied getTemp API. You can append the reading to a log file, say temperature.log. Since you will only need to keep the most recent hour of readings, buffer the last 60 readings, and then just overwrite the log file with the buffered readings. Next, call a program, for example, a Python script called getstats.py, which calculates the temperature stats from the 60-minute log and loads the resulting stats into the reporting system using the loadstats API. The stats can then be used to display a live chart showing the hourly min, max, and average temperatures. You will also want to schedule your workflow to run every minute. Start by creating a shell script called temperature_etl.sh. You can create the file by using the touch command. Next, open the file with any text editor such as gedit. In the editor, type in the bash shebang to turn your file into a bash shell script. Now you can add the following comments to help outline your tasks. Extract a temperature reading from the sensor using the supplied getTemp API. Append the reading to a log file, say temperature.log. You only need to keep the most recent hour of readings, so buffer the last 60 readings. Call a program, say a Python script called getStats.py, which calculates the temperature stats from the 60-minute log, and load the resulting stats into the reporting system using the supplied API. After you finish writing the ETL bash script, you will need to schedule it to run every minute. Now you can fill in some details for your task comments. Start by initializing your temperature log file on the command line with the touch command. In the text editor, enter a command to call the API to read a temperature and append the reading to the temperature log. Now, just keep the last hour, or 60 lines, of your log file by overwriting the temperature log with its last 60 lines. This completes the data extraction step. Suppose you have written a Python script called getStats.py, which reads temperatures from a log file, calculates the temperature stats, and writes the results to an output file so that the input and output file names are specified as command line arguments. You can add the following line to your ETL script, which calls Python 3 and invokes your Python script getStats.py using the readings in temperature.log and writes the temperature stats to a CSV file called temperaturestats.csv. This completes the transformation component of your ETL script. Finally, you can load the resulting stats into the reporting system using the supplied API by calling the API and specifying the temperature stats CSV as a command line argument. Next, don't forget to set permissions to make your shell script executable. Now it's time to schedule your ETL job. Open the cron tab editor, schedule your job to run every minute of every day, close the editor and save your edits. Your new ETL job is now scheduled and running in production. In this video, you learned that ETL pipelines can be built from basic bash scripts. And an ETL job can be scheduled to run by creating a cron job for your bash script. Welcome to Introduction to Data Pipelines. After watching this video, you will be able to define what a pipeline is, describe data pipeline performance in terms of latency and throughput, and give examples of data pipeline use cases. The concept of a pipeline applies broadly to any set of processes that are connected to each other sequentially. This means that the output of one process is passed along as input to the next process in a chain. For example, one way to move boxes from one place to another is to have a chain of friends, each passing the boxes, one by one, up the line to the nearest friend. Each friend is a processor whose function is identical: get a box, pass a box. Mass production is similar, but transformations may differ from stage to stage. Data pipelines are pipelines that specifically move or modify data. The purpose of a data pipeline is to move data from one place or form to another. A data pipeline is a system which extracts data and passes it along to optional transformation stages for final loading. This includes low-level hardware architectures, but our focus here is on data pipelines as architectures driven by software processes, such as commands, programs, and processing threads. The simple bash pipe command in Linux can be used as the glue that connects such processes together. We can think of data flowing through a pipeline in the form of data packets, a term which we will use to broadly refer to units of data. Packets can range in size from a single record or event to large collections of data. Here, we have data packets queued for ingestion to the pipeline. The length of the data pipeline represents the time it takes for a single packet to traverse the pipeline. The arrows between packets represent the throughput delays, or the times between successive packet arrivals. You have just been introduced to two key performance considerations regarding data pipelines. The first is latency, which is the total time it takes for a single packet of data to pass through the pipeline. Equivalently, latency is the sum of the individual time spent during each processing stage within the pipeline. Thus, overall latency is limited by the slowest process in the pipeline. For example, no matter how fast your internet service is, the time it takes to load a web page will be decided by the server speed. The second performance consideration is called throughput. It refers to how much data can be fed through the pipeline per unit of time. Processing larger packets per unit of time increases throughput. Coming back to our example of having a chain of friends passing boxes from one to another, we can see in the right image, within limits, that passing bigger boxes can increase productivity. Let's list a few of the applications of data pipelines from the multitude of use cases. The simplest pipeline is one which has no transformations and is used to copy data from one location to another as in-file backups, integrating disparate raw data sources into a data lake, moving transactional records to a data warehouse, streaming data from IoT devices to make information available in the form of dashboards or alerting systems, preparing raw data for machine learning development or production, and message sending and receiving, such as with email, SMS, or online video meetings. In this video, you learned that the purpose of a data pipeline is to move data from one place or form to another. We can visualize data flowing through a pipeline as a series of data packets flowing in and out one by one. Latency and throughput are key design considerations for data pipelines. And use cases for data pipelines are many and range from simple copy and paste like data backups to online video meetings. Welcome to Key Data Pipeline Processes. After watching this video, you will be able to list key data pipeline processes, describe data pipeline monitoring considerations, and describe data pipeline solutions for mitigating data flow bottlenecks. Data pipeline processes typically have the following stages in common: extraction of data from one or more data sources, ingestion of the extracted data into the pipeline, optional data transformation stages within the pipeline, and final loading of the data into a destination facility, a mechanism for scheduling or triggering jobs to run, monitoring the entire workflow, and maintenance and optimization as required to keep the pipeline up and running smoothly. The data pipeline needs to be monitored once it is in production to ensure data integrity. Some key monitoring considerations include latency, or the time it takes for data packets to flow through the pipeline, throughput demand, the volume of data passing through the pipeline over time, errors and failures caused by factors such as network overloading and failures at the source or destination systems, utilization rate, or how fully the pipeline's resources are being utilized, which affects cost. And lastly, the pipeline should also have a system for logging events and alerting administrators when failures occur. Ideally, at the moment one stage has completed its process on a packet of data, the next packet in the queue would be available to it just in time. In that case, the stage is never left to idle while the pipeline is operating and there are no upstream bottlenecks. Extending this notion to all stages of the pipeline implies that all stages should take the same amount of time to process a packet. This means that there are no bottlenecks and we can say that the entire pipeline has been load balanced. Let's take a closer look at this idea. Suppose your pipeline has a bottleneck in one of its stages, such as the longer red section here, which has more latency than the other stages in the pipeline. If it's possible to parallelize that stage, for example by splitting the data into two concurrent stages, like this, then you can reduce this stage's latency. There will be a little overhead in managing the parallelization and recombination of the output back into the pipeline, but the overall latency will be reduced. Due to the time and cost considerations, pipelines are rarely perfectly load balanced. This means there will almost always be stages which are bottlenecks in the data flow. If such a stage can be parallelized, then it can be sped up to align better with the flow rate. A simple way to parallelize a process is to replicate it on multiple CPUs, cores, or threads, and distribute data packets as they arrive in an alternating fashion amongst the replicated channels. Pipelines that incorporate parallelism are referred to as being dynamic or nonlinear, as opposed to static, which applies to serial pipelines. Further synchronization between stages is likely still possible, and a typical solution is to include input and output, or I/O buffers, as needed to smooth out the flow of data. An I/O buffer is a holding area for data, placed between processing stages having different or varying delays. Buffers can also be used to regulate the output of stages having variable processing rates, and thus may be used to improve throughput. Single input and output buffers are also used to distribute and gather loads on parallelized stages. In this video, you learned that in addition to extraction, transformation, and loading, data pipeline processes include scheduling, triggering, monitoring, maintenance, and optimization. Pipeline monitoring considerations include tracking latency, throughput, resource utilization, and failures. And finally, unbalanced or varying loads can be mitigated by introducing parallelization and I/O buffers at bottlenecks. Welcome to batch versus streaming data pipeline use cases. After watching this video, you will be able to differentiate between batch and streaming data pipelines, describe microbatch and hybrid lambda data pipelines, list use cases for batch data pipelines, and list use cases for streaming data pipelines. Batch data pipelines are used when datasets need to be extracted and operated on as one big unit. Batch processes typically operate periodically on a fixed schedule, ranging from hours to weeks apart. They can also be initiated based on triggers, such as when the data accumulating at the source reaches a certain size. Batch processes are appropriate for cases which don't depend on recency of data. Typically, batch data pipelines are employed when accuracy is critical, but competitive mission-critical streaming technologies are rapidly maturing. Streaming data pipelines are designed to ingest packets of information, such as individual credit card transactions or social media activities, one by one in rapid succession. Stream processing is used when results are required with minimal latency, essentially in real time. With streaming pipelines, records or events are processed immediately as they occur. Event streams can also be appended to storage to build up a history for later use. Users, including other software systems, can publish or write and subscribe to or read event streams. By decreasing the batch size and increasing the refresh rate of individual batch processes, you can achieve near real-time processing. Using microbatches may also help with load balancing, leading to lower overall latency, useful when only very short windows of data are required for transformations. The use case differences between batch and stream processing come down to a trade-off between accuracy and latency requirements. With batch processing, for example, data can be cleaned, and thus you can get higher quality output, but this comes at the cost of increased latency. If you require low latency, your tolerance for faults likely has to increase. A Lambda architecture is a hybrid architecture designed for handling big data. Lambda architectures combine batch and streaming data pipeline methods. Historical data is delivered in batches to the batch layer, and real-time data is streamed to a speed layer. These two layers are then integrated in the serving layer. The data stream is used to fill in the latency gap caused by the processing in the batch layer. Lambda can be used in cases where access to earlier data is required, but speed is also important. A downside to this approach is the complexity involved in the design. You usually choose a Lambda architecture when you are aiming for accuracy and speed. Example use cases for batch data pipelines include periodic data backups and transaction history loading, processing of customer orders and billing, data modeling on slowly varying data, mid to long-range sales forecasting and weather forecasting, analysis of historical data, and diagnostic medical image processing. Use cases for streaming data pipelines are on the rise and include cases such as watching movies and listening to music or podcasts, social media feeds and sentiment analysis, fraud detection, user behavior analysis and targeted advertising, stock market trading, real-time product pricing, and recommender systems. In this video, you learned that batch pipelines extract and operate on batches of data. Batch processing is used when accuracy is critical or there is no need for the most recent data. Streaming data pipelines ingest data packets one by one in rapid succession. Streaming pipelines are used when the most current data is needed. Microbatch processing can be used to simulate real-time data streaming. And Lambda architecture can be used in cases where access to earlier data is required, but speed is also important. Welcome to Data Pipeline Tools and Technologies. After watching this video, you will be able to discuss data pipeline technologies, list open source and enterprise ETL and ELT tools, and list streaming data pipeline tools. There are many open source and commercial data pipeline tools and cloud services to consider. Typical features of modern enterprise-grade ETL and ELT products include the following: fully automated data pipeline creation, from data extraction to loading in the destination. Ease of use. Rule recommendations for extracting, transforming, and loading data. Some tools even crawl your data. A drag-and-drop GUI for specifying rules and data pipeline flows, also known as no-code ETL. Transformation support for and assistance with complex transformations, such as operations on strings, calculations, and merging data. And security and compliance. Modern tools encrypt both data in transit and at rest and are certified compliant with industry and government regulations like HIPAA and GDPR. Python, along with the Pandas library, is a very popular and highly versatile programming environment for building data pipelines. Pandas uses a data structure called a data frame to handle Excel or CSV-style tabular data. It's a great tool for prototyping ETL pipelines and for exploratory data analysis, but it can be challenging to scale to big data since data frame manipulations must be carried out in memory. Libraries with similar data frame APIs include Dask, Viex, and Apache Spark, which can all help you to scale up to big data. For scalability, consider SQL-like alternatives to data frame APIs such as PostgreSQL. Apache Airflow, another package based on the Python programming language, is a highly versatile and well-known example of an open-source configuration-as-code data pipeline platform. Apache Airflow was open-sourced by Airbnb and was created to programmatically author, schedule, and monitor data pipeline workflows. It was designed to be scalable and can handle an arbitrary number of parallel compute nodes. And Airflow integrates with most cloud platforms, including AWS, IBM, Google Cloud, and Microsoft Azure. Talend Open Studio is yet another open-source data pipeline development and deployment platform. Talend Open Studio supports big data migration, data warehousing, and profiling, and it includes collaboration, monitoring, and scheduling capabilities. It also has an interactive drag-and-drop GUI which allows you to create ETL pipelines. There is no need to write code, as Java code is automatically generated. It also connects to many data warehouses such as Google Sheets, RDBMS, IBM DB2, and Oracle. Amongst the many enterprise data pipeline tools, AWS Glue is a fully managed ETL service that makes it easy for you to prepare and load your data for analytics. Glue crawls your data sources to discover data formats and suggests schemas to store your data, and you can quickly create and run an ETL job using the AWS console. Panoply is another enterprise solution, but its focus is on ELT rather than ETL. It handles data connection and integration without code and comes with SQL functionality so you can generate views of your data. This frees your time to focus on data analysis rather than optimizing your data pipeline. Panoply also integrates with many dashboard and BI tools, including Tableau and Power BI. Alteryx is another well-known commercial data pipeline tool. Alteryx is also a highly versatile self-service data analytics platform with multiple products. It gives you drag-and-drop accessibility to built-in ETL tools, and you don't need to know SQL or programming to create and maintain a complex data pipeline. IBM InfoSphere Data Stage is a data integration tool for designing, developing, and running both ETL and ELT pipelines. InfoSphere Data Stage is the data integration component of IBM InfoSphere Information Server. Like many other platforms, it also provides a drag-and-drop framework for developing workflows. InfoSphere Data Stage also uses parallel processing and enterprise connectivity to provide a truly scalable platform. IBM Streams is a streaming data pipeline technology which enables you to build real-time analytical applications using the Streams Processing Language, or SPL, plus Java, Python, or C++. You can use it to blend data in motion with data at rest to deliver continuous intelligence in real time. Streams powers a stream analytics service that allows you to ingest and analyze millions of events per second with sub-millisecond latency, and IBM Streams comes packaged with IBM Stream Flows, a tool which allows you to drag and drop operators onto a canvas and modify parameters from built-in settings panels. There are many other stream processing technologies to consider, including Apache Storm, SQL Stream, Apache Samsa, Apache Spark, Azure Stream Analytics, and Apache Kafka. In this video, you learned that modern enterprise-grade data pipeline tools include technologies such as transformation support, drag-and-drop GUIs, and security and compliance features. Pandas, Viex, and Dask are useful open-source Python libraries for prototyping and building data pipelines. Apache Airflow and Talend Open Studio allow you to programmatically author, schedule, and monitor big data workflows, and that Panoply is specific to ELT pipelines, while tools such as Alteryx and IBM InfoSphere Data Stage can handle both ETL and ELT workflows. You also learned that stream processing technologies include Apache Kafka, IBM Streams, SQL Stream, and Apache Spark. Welcome to Apache Airflow Overview. After watching this video, you will be able to recognize Apache Airflow as a platform to programmatically author, schedule, and monitor workflows, list the main features and principles of Apache Airflow, and list common use cases for Apache Airflow. Apache Airflow is a great open-source workflow orchestration tool that is supported by an active community. It is a platform that lets you build and run workflows, such as batch data pipelines. With Apache Airflow, a workflow is represented as a DAG, a directed acyclic graph, and contains individual pieces of work called tasks arranged with dependencies. And note that unlike big data tools such as Apache Kafka, Apache Storm, Apache Spark, or Flink, Apache Airflow is not a data streaming solution. It is primarily a workflow manager. Let's take a look at a simplified overview of Apache Airflow's basic components. Airflow comes with a built-in scheduler which handles the triggering of all scheduled workflows. The scheduler is responsible for submitting individual tasks from each scheduled workflow to the executor. The executor handles the running of these tasks by assigning them to workers, which then run the tasks. The web server serves Airflow's powerful interactive user interface. From this UI, you can inspect, trigger, and debug any of your DAGs and their individual tasks. The DAG directory contains all of your DAG files, ready to be accessed by the scheduler, the executor, and each of its employed workers. Finally, Airflow hosts a metadata database which is used by the scheduler, executor, and the web server to store the state of each DAG and its tasks. A DAG specifies the dependencies between tasks and the order in which to execute them. The tasks themselves describe what to do. In this example DAG, the tasks include data ingestion, data analysis, saving the data, generating reports, and triggering other systems, such as reporting any errors by email. Let's have a look at the life cycle of a task's state. In this diagram, you can see how Apache Airflow might assign states to a task during its life cycle. No status. The task has not yet been queued for execution. Scheduled. The scheduler has determined that the task's dependencies are met and has scheduled it to run. Removed. For some reason, the task has vanished from the DAG since the run started. Upstream failed. An upstream task has failed. Queued. The task has been assigned to the executor and is waiting for a worker to become available. Running. The task is being run by a worker. Success. The task is finished running without errors. Failed. The task had an error during execution and failed to run. And up for retry. The task failed but has retry attempts left and will be rescheduled. Ideally, a task should flow through the scheduler from no status to scheduled to queued to running and finally to success. Now, let's have a look at the 5 main features and benefits of Apache Airflow. Pure Python. Create your workflows using standard Python. This allows you to maintain full flexibility when building your data pipelines. Useful UI. Monitor, schedule, and manage your workflows via a sophisticated web app offering you full insight into the status of your tasks. Integration. Apache Airflow provides many plug-and-play integrations, such as IBM Cloudant, that are ready to execute your tasks. Easy to use. Anyone with Python knowledge can deploy a workflow. Airflow does not limit the scope of your pipelines. And finally, the open source feature. Whenever you want to share your improvement, you can do this by opening a pull request. Airflow has many active users who are sharing their experiences in the Apache Airflow community. Apache Airflow pipelines are built on 4 main principles. They are scalable. Airflow has a modular architecture and uses a message queue to orchestrate an arbitrary number of workers. It is ready to scale to infinity. Dynamic. Airflow pipelines are defined in Python and allow dynamic pipeline generation. Thus, your pipelines can contain multiple simultaneous tasks. Extensible. You can easily define your own operators and extend libraries to suit your environment. And lean. Airflow pipelines are lean and explicit. Parameterization is built into its core using the powerful Jinja templating engine. Apache Airflow has supported many companies in reaching their goals. For example, Sift used Airflow for defining and organizing machine learning pipeline dependencies. SeniorLink increased the visibility of their batch processes and decoupled them. Xperity deployed Airflow as an enterprise scheduling tool, and OneFootball used Airflow to orchestrate SQL transformations in their data warehouses and to send daily analytics emails. In this video, you learned that Apache Airflow is a platform to programmatically author, schedule, and monitor workflows. The 5 main features of Airflow are its use of Python, its intuitive and useful user interface, extensive plug-and-play integrations, ease of use, and the fact that it is open source. You also learned that Apache Airflow is scalable, dynamic, extensible, and lean. And finally, defining and organizing machine learning pipeline dependencies with Apache Airflow is one of the common use cases. Welcome to Advantages of Representing Data Pipelines as DAGs in Apache Airflow. After watching this video, you will be able to define what a directed acyclic graph or DAG is, describe workflows as DAGs of tasks and dependencies, outline the components of a DAG definition file, describe how Apache Airflow Scheduler executes tasks on an array of workers, and list key advantages of defining workflows as code. A DAG is a special kind of graph called a directed acyclic graph. A simple graph consists of nodes and edges, like this. Here, the circles are called nodes, and the lines connecting pairs of nodes are called edges. A directed graph is also a graph, but it has more structure. As you can see here, each edge has a specified direction. It connects a starting node with another node. And lastly, the acyclic part means there are no loops or sequences of directed edges that return to a node in the chain, such as the red cycle shown here. Let's take a look at a few examples of DAGs. The simplest, non-trivial DAG has a single directed edge and looks like this. It has a single root node, which is connected to a single terminal node. Here's another DAG, which we've already seen. It also has single root and terminal nodes. Here's an example of a tree, which is a commonly used graph for representing family trees or directory structures. All trees are DAGs, but not all DAGs are trees. For example, this DAG is not a tree since it has more than one root node. A DAG doesn't impose those restrictions, so a single node can have multiple parents, and there may be multiple nodes with no parents. DAGs are used to represent workflows or pipelines in Apache Airflow. Each task performed by your data pipeline is represented as a node in a DAG, while each of the dependencies between two tasks in your pipeline are represented as a directed edge in the DAG. In other words, edges define the order in which the two tasks should run. Thus, DAGs are used in Airflow to define what tasks should run and in what sequence they should run. A DAG is defined in a Python script, which represents the DAG structure. Thus, the tasks and their dependencies are defined as code. Also, scheduling instructions are specified as code in the DAG script. Let's take a closer look at the nodes or tasks in a DAG. Just like the DAG itself, each task performed within your DAG is also written in Python. Each task implements an operator. For example, a Python operator is used to deploy some Python code, a SQL operator to run a SQL query, and a bash operator can be used to run a bash command. Operators are used to define what each task in your DAG does. Sensors are a class of operators which are used to poll for a certain time or condition to be met. For example, you can use a sensor to check every 30 seconds whether a file exists or whether another DAG has finished running. There are many other types of operators, including email and HTTP request operators. An Apache Airflow DAG is a Python script consisting of the following logical blocks: library imports, DAG arguments, DAG definition, task definitions, and task pipeline. Let's briefly go over an example. The first block of your DAG definition script is where you import any Python libraries that you require. For example, the from Airflow import DAG command to import the DAG module from the Airflow collection. The next block of code is for specifying default arguments for your DAG, such as its default start date. Next comes the DAG definition, or instantiation block for your DAG, which specifies things like your default arguments. Continuing along with our example DAG code, individual task definitions, which are the nodes of the DAG, form your DAG's next building block. In this example, we have 2 tasks, which happen to be bash operators. Finally, the task pipeline specifies the dependencies between your tasks. Here, task 2 depends on the result of task 1, and this forms the last logical block of your DAG script. Your new DAG has been created, but it hasn't yet been deployed. To that end, Airflow Scheduler is designed to run as a persistent service within the Airflow production environment. Apache Airflow Scheduler can be used to deploy your workflow on an array of workers. It follows the tasks and dependencies that you specified in your DAG. Once you start an Airflow Scheduler instance, your DAGs will start running based on the start date you specified as code in each of your DAGs. After that, the scheduler triggers each subsequent DAG run according to the schedule interval that you specified. One of the key advantages of Apache Airflow's approach to representing data pipelines as DAGs is the fact that they are expressed as code. When workflows are defined as code, they become more maintainable. Developers can follow explicitly what has been specified by reading the code. Versionable. Code revisions can easily be tracked by a version control system, such as Git. Collaborative. Teams of developers can easily collaborate on both development and maintenance of the code for the entire workflow. And testable. Any revisions can be passed through unit tests to ensure the code still works as intended. In this video, you learned that in Apache Airflow, DAGs are workflows defined as Python code. Tasks, which are nodes in your DAG, are created by implementing Airflow's built-in operators. Pipelines are specified as dependencies between tasks, which are the directed edges between nodes in your DAG. Airflow Scheduler schedules and deploys your DAGs. And finally, the key advantage of Apache Airflow's approach to representing data pipelines as DAGs is the fact that they are expressed as code. Accordingly, it makes your data pipelines more maintainable, testable, and collaborative. Welcome to Apache Airflow UI. After watching this video, you will be able to identify current DAGs in your environment, list different ways to visualize a specific DAG, review the code that defines your DAG, analyze the duration of each task in your DAG over multiple runs, and select context metadata for any task instance. Here's what the landing page for the Apache Airflow user interface looks like in your browser. It defaults to the DAGs view, which is a table containing data about each DAG in your environment. Each row displays interactive information about a DAG in your environment, such as each DAG's name, its run schedule, in this case in the cron tab format, the DAG's owner, this one is a built-in example from Airflow, the status of the tasks from the current or most recent DAG run, the status of all previous DAG runs, plus a collection of quick links to drill down into more information related to the DAG. On the far left, you can drill down to access more interactive details, and in the next column you can toggle to pause a DAG. All of the DAGs here are currently not running. You can visualize DAGs in several ways as follows. Start by clicking on the name of the DAG you want to visualize. This DAG, called Simple Example, happens to be running in production, as you can see here by the On button. Your DAG's tree view opens by default when you click on its name. It shows a timeline of the status of your DAG and its tasks for each run. Here, you can select the base date and the number of runs to display. Each status is color-coded according to the legend displayed here. You can also hover your mouse pointer over any task in the timeline to view more information about it. Here's another DAG, this time displayed in graph view. At the bottom of the screen, you can see your DAG's tasks and dependencies. Each task is color-coded by its operator type according to this legend. Here, you can filter your view by toggling these status option buttons. The task instance context menu can be accessed from any of these kinds of views, that is, views that display task instances for your DAG. This menu allows you, for example, to drill down on a selected task instance to view and edit many details about it, or to view the log file for your task. By clicking on the Code button, you can also view the complete Python source code that defines your DAG. Here we see the building blocks of your DAG, for example, the library imports and the individual task definitions which invoke bash operators in this case. By clicking on Task Duration, you can view a timeline chart of your DAG's task durations to see how they have been performing. Here you can toggle the tasks that you wish to highlight the last N runs for. In this video, you learned that Apache Airflow has a rich UI that simplifies working with data pipelines. You can visualize your DAG in several informative ways, including both graph and tree mode. You can also review the Python code that originally defined your DAG. You can analyze the duration of each task in your DAG over multiple runs. And finally, you can select context metadata for any task instance. Welcome to Build a DAG using Airflow. After watching this video, you will be able to interpret an Airflow pipeline as a Python script that defines an Airflow DAG object, list the key components of a DAG definition file, create tasks by instantiating operators in your DAG definition file, and set up dependencies amongst tasks. An Apache Airflow DAG is a Python script which consists of the following logical blocks: Python library imports, DAG argument specification, the DAG definition or instantiation, individual task definitions, which are the nodes of the DAG, and finally, the task pipeline, which specifies the dependencies between tasks. Let's implement a simple Apache Airflow pipeline by writing a DAG definition script. We will create a very simple pipeline called simpleexampledag.py that prints a greeting and then prints the current date and time. We will also schedule it to repeat the process every 5 seconds. Let's go through the list of logical blocks one by one. Begin by importing the Python libraries you will need for your DAG. Here, start by importing the DAG class from the Airflow library. Then the bash operator, which you will use to create the 2 print tasks, and the date-time module, which you will need for specifying several time-related parameters. The next block is for specifying the default DAG arguments. Notice that they are specified as a Python dict, which is just a collection of key-value pairs enclosed by curly braces. These are used to specify such things as the owner of the DAG, which is you, and its start date, in this case July 28, 2021. The number of times it should keep trying if it is failing, here only once if it does fail, and the retry delay, or the time to wait between subsequent tries, which in this case is 5 minutes. This next block is used for instantiating your workflow as a DAG object. Here you can specify things like the name of your DAG, simple example, a description of your workflow, for example, a simple example DAG, the default arguments to apply to your DAG, which in this case are specified by the default args dict you already defined above, and finally, scheduling instructions. In this case, the DAG will run repeatedly on a schedule interval of 5 seconds once it is deployed. Next comes the task definition block. Here we define 2 tasks, task 1 and task 2, both of which are bash operators. Their respective IDs are specified as print hello and print date. They each call a bash command where the first task will echo greetings, the date and time are, and the second task will print the current date and time using the bash command date. Finally, each task is assigned to the DAG you instantiated in the DAG definition block above. The final block is where you specify the dependencies for your workflow, like this. Here, the double greater than notation specifies that task 2 is downstream from task 1. This means the task 1, which we named print hello, will run first, And once print hello runs successfully, task 2 or print date will run. This completes the creation of your Airflow DAG, and you now have a good idea of the general pattern. In this video, you learned that an Airflow pipeline is a Python script that instantiates an Airflow DAG object. Key components of a DAG definition file are library imports, DAG arguments, DAG and task definitions, and the task pipeline specification. You can specify a schedule interval in your DAG definition if you want it to run repeatedly by setting the schedule interval parameter. And finally, tasks are instantiated operators imported from the Apache Airflow Operators module. Welcome to Airflow Logging and Monitoring. After watching this video, you will be able to use logging capabilities to monitor the status and diagnose problems with DAG runs, and explain accessing emitted metrics such as counters, gauges, and timers. The logging capability is required for developers to monitor the status of tasks in DAG runs and to diagnose and debug issues. By default, Airflow logs are saved to local file systems as log files. This makes it convenient for developers to quickly review the log files, especially in a development environment. For Airflow production deployments, the log files can also be sent to cloud storage, such as IBM Cloud, AWS, or Azure for remote accessing. The log files can also be sent to search engines and dashboards for further retrieval and analysis. Airflow recommends using Elasticsearch and Splunk, which are two popular document database and search engines to index, search, and analyze log files. By default, log files are organized by DAG IDs and task IDs, and you can find a specific log file for a task execution using the following path convention: logs/DAG_ID/task_ID/execution_date/try_number.log. For example, suppose you want to find the log for the first execution try of task 1 in a dummy DAG at a specific time. You can go to the folder logs/dummy_dag/task1/execution_date/1.log. And if you click the first log file, you can check a lot of useful information, such as the running command, command results, task results, and so on. You can also quickly review the task events via UI provided by the Airflow web server. You can search events with fields like DAG ID, task ID, and execution date, and quickly get an overview of the specific DAGs and tasks you're looking for. Airflow produces 3 different types of metrics for checking and monitoring components' health. These are counters, gauges, and timers. Counters are metrics that will always be increasing, such as the total counts of successful or failed tasks. Gauges are metrics that may fluctuate, for example, the number of currently running tasks or DAG bag sizes. Timers are metrics related to time duration. For instance, the time to finish a task or the time for a task to reach a success or failed state. Similar to logs, the metrics produced in Airflow production deployments should be sent and analyzed by dedicated repositories and tools. Airflow recommends using StatsD, which is a network daemon that can gather metrics from Airflow and send them to a dedicated metrics monitoring system. For metrics monitoring and analysis, Airflow recommends using Prometheus, which is a popular metrics monitoring and analysis system. Prometheus can also aggregate and visualize metrics in a dashboard for more interactive visual analytics. In this video, you learned that you can save Airflow logs into local file systems and save them to cloud storage, search engines, and log analyzers. Airflow recommends sending production deployment logs to be analyzed by Elasticsearch or Splunk. With Airflow's UI, you can view DAGs and task events easily. You also learned that the 3 types of Airflow metrics are counters, gauges, and timers. And finally, Airflow recommends that you send production deployment metrics for analysis by Prometheus via StatsD. Welcome to Distributed Event Streaming Platform Components. After watching this video, you will be able to describe what an event is, list the common event formats, describe what an event stream platform or ESP is, list the main components of an ESP, and list the popular ESPs. An event normally means something worth noticing is happening. In the context of event streaming, an event is a type of data which describes the entity's observable state updates over time. For example, the GPS coordinates of a moving car, the temperature of a room, blood pressure measurements of a patient, or RAM usage of a running application. An event, as a special type of data, has different formats. Let's have a look at the three most common formats. It can be as a primitive type, such as a plain text, number, or date, or an event may be in key value format, and its value can be a primitive data type, or a complex data type like list, tuple, JSON, XML, or even bytes. For example, the coordinates tuple of a car with car ID 1. Also, very often an event can be associated with a timestamp to make it time-sensitive. Next, we have a closer look at event streaming. Suppose we have one event source, such as a group of sensors, a monitoring device, a database, or a running application. This event source may continuously generate a large event volume at a short time interval or nearly real time. Those real-time events need to be properly transported to an event destination, such as a file system, another external database, or an application. The continuous event transportation between an event source and an event destination is called event streaming. After all that you have learned about ETL so far, you may think that to implement such an ETL process between one event source to one event destination should be straightforward. However, what if we have multiple different event sources and destinations? In a real-world scenario, event streaming can be really complicated with multiple distributed event sources and destinations, as data transfer pipelines may be based on different communication protocols, such as FTP, File Transfer Protocol, HTTP, Hypertext Transfer Protocol, JDBC, Java Database Connectivity, SCP, Secure Copy, and so on. An event destination can also be an event source simultaneously. For example, one application could receive an event stream and process it, then transport the processed results as an event stream to another destination. To overcome such a challenge of handling different event sources and destinations, we will need to employ the Event Stream Platform, or ESP. An ESP acts as a middle layer among various event sources and destinations and provides a unified interface for handling event-based ETL. As such, all event sources only need to send events to an ESP instead of sending them to the individual event destination. On the other side, event destinations only need to subscribe to an ESP and just consume the events sent from the ESP instead of the individual event source. Different ESPs may have different architectures and components. Here, we show you some common components included in most ESP systems. The first and foremost component is the event broker, which is designed to receive and consume events. Since it is the core component of an ESP, we will explain it in more detail in the next slide. The second common component of an ESP is event storage, which is used for storing events being received from event sources. Accordingly, event destinations do not need to synchronize with event sources, and stored events can be retrieved at will. The third common component is the analytic and query engine, which is used for querying and analyzing the stored events. Let's have a look at the event broker, which is the core component of an ESP. It normally contains three subcomponents: ingester, processor, and consumption. The ingester is designed to efficiently receive events from various event sources. The processor performs operations on data such as serializing and deserializing, compressing and decompressing, encryption and decryption, and so on. The consumption component retrieves events from event storage and efficiently distributes them to subscribed event destinations. There are many ESP solutions, including Apache Kafka, Amazon Kinesis, Apache Flink, Apache Spark, Apache Storm, and more, such as Logstash, Inelastic Stack, and so on. Each has its unique features and application scenarios. Among these ESPs, Apache Kafka is probably the most popular one. In this video, you learned that an event stream represents entity status updates over time. Common event formats include primitive data types, key value, and key value with a timestamp. An ESP is needed especially when there are multiple event sources and destinations. The main components of an ESP are event broker, event storage, analytic, and query engine. Apache Kafka is the most popular open-source ESP. And finally, popular ESPs include Apache Kafka, Amazon Kinesis, Apache Flink, Apache Spark, Apache Storm, and more. Welcome to Apache Kafka Overview. After watching this video, you will be able to recognize Apache Kafka as an event streaming platform or ESP, describe the architecture of Apache Kafka, list common use cases for Apache Kafka, summarize the main features and benefits of Apache Kafka, and list popular Kafka-based ESP as a service providers. By now, you should be able to describe what an event streaming platform and its core components are, and may think that it must be extremely difficult to implement an ESP from scratch. That is true, but we already have many great open source and commercial ESP solutions available that come with many built-in capabilities. Among these, Apache Kafka, an open source project, has probably the most popular event streaming platform. Kafka is a comprehensive platform and can be used in many application scenarios. Let's look at some of the common ones here. Kafka was originally used to track user activities such as keyboard strokes, mouse clicks, page views, searches, gestures, screen time, and so on. But now it is also suitable for all kinds of metric streaming such as sensor readings, GPS, as well as hardware and software monitoring. For enterprise applications and infrastructure with a huge number of logs, Kafka can be used to collect and integrate them into a centralized repository. For banks, insurance, or fintech companies, Kafka is also widely used for payments and transactions. These scenarios are just the tip of the iceberg. You basically can use Kafka in scenarios when you want high throughput and reliable data transportation services among various event sources and destinations. All of these events will be ingested in Kafka and become available for subscriptions and consumption, including further data storage and movement to other online and offline databases and backups, real-time processing and analytics, including dashboard, machine learning, AI algorithms, and so on, generating notifications such as email, text messages, and instant messages, or data governance and auditing to make sure sensitive data, such as bank transactions, are complying with regulations. Kafka has a distributed client-server architecture. For the server side, Kafka is a cluster with many associated servers called brokers, acting as the event broker to receive, store, and distribute events. All those brokers are managed by another distributed system called Zookeeper to ensure all brokers work in an efficient and collaborative way. Kafka uses a TCP, or Transmission Control Protocol-based network communication protocol to exchange data between clients and servers. For the client side, Kafka provides different types of clients, such as Kafka CLI, Command Line Interface, which is a collection of shell scripts to communicate with the Kafka server, many high-level programming APIs such as Java, Scala, REST APIs, and some specific third-party clients made by the Kafka community. Accordingly, you could choose different clients based on your requirements. Now that you have a basic understanding of Kafka, let's see why Apache Kafka has become such a popular ESP. Kafka has the following main features. It is a distribution system, which makes it highly scalable to handle high data throughput and concurrency. A Kafka cluster normally has multiple event brokers, which can handle event streaming in parallel, and as such, Kafka is very fast and highly scalable. Kafka also divides event storage into multiple partitions and replications, which makes it fault-tolerant and highly reliable. Kafka stores the events permanently. As such, event consumption could be done whenever suitable for consumers without a deadline. And Kafka is open source, meaning that you can use it for free and even customize it based on your specific requirements. Even though Kafka is open source and well documented, it is still challenging to configure and deploy a Kafka without professional assistance. Deploying a Kafka cluster requires extensive efforts for tuning infrastructure and consistently adjusting the configurations, especially for enterprise-level deployments. Fortunately, several commercial service providers offer an on-demand ESP as a service to meet your streaming requirements. Many of them are built on top of Kafka and provide added value for customers. Some well-known ESP providers include Confluent Cloud, which provides customers with fully managed Kafka services either on-premises or on cloud. IBM Event Streams, which is also based on Kafka and provides many add-on services such as enterprise-grade security, disaster recovery, and 24/7 cluster monitoring. And Amazon Managed Streaming for Apache Kafka, which is also a fully managed service to facilitate the build and deployment of Kafka. In this video, you learned that Apache Kafka is one of the most popular open-source ESPs. Common Kafka use cases include user activity tracking, metrics and logs integrations, and financial transaction processing. Apache Kafka is a highly scalable and reliable platform that stores events permanently. And finally, popular Kafka-based ESP service providers include Confluent Cloud, IBM Event Streams, and Amazon Managed Streaming. Welcome to Building Event Streaming Pipelines Using Kafka. After watching this video, you will be able to describe the core components of Kafka, use Kafka to publish or write and subscribe to or read streams of events, use Kafka to consume events either as they occur or retrospectively, and describe an end-to-end event streaming pipeline example. A Kafka cluster contains one or many brokers. You may think of a Kafka broker as a dedicated server to receive, store, process, and distribute events. Brokers are synchronized and managed by another dedicated server called Zookeeper. For example, here we have a log topic and a transaction topic in broker 0, a payment topic and a GPS topic in broker 1, and a user click topic and a user search topic in broker 2. Each broker contains one or many topics. You can think of a topic as a database to store specific types of events, such as logs, transactions, and metrics, for example. Brokers manage to save published events into topics and distribute the events to subscribed consumers. Like many other distribution systems, Kafka implements the concepts of partitioning and replicating. It uses topic partitions and replications to increase fault tolerance and throughput so that event publication and consumption can be done in parallel and with multiple brokers. In addition, even if some brokers are down, Kafka clients are still able to work with the target topics replicated in other working brokers. For example, a log topic has been separated into two partitions, 0, 1. And a user topic has been separated into two partitions, 0, 1, and each topic partition is duplicated into two replications and stored in different brokers. The Kafka CLI, or Command Line Interface Client, provides a collection of powerful script files for users to build an event streaming pipeline. The Kafka topic script is the one you will probably be using often to manage topics in a Kafka cluster. It is straightforward. Let's have a look at some common usages. The first one is to create a topic. Here, we are trying to create a topic called log_topic with 2 partitions and 2 replications. One important note here is that many Kafka commands, like conf topics, require users to refer to a running Kafka cluster with a host and a port, such as a local host with a port 9092. After you have created some topics, you can check all created topics in the cluster using the list option. And if you want to check more details of a topic, such as partitions and replications, you can use the describe option. And you can delete a topic using the delete option. Next, you will find out more about publishing events using Kafka producers. Features of a Kafka producer. They are client applications that publish events to topic partitions according to the same order as they are published. When publishing an event in Kafka Producer, an event can be optionally associated with a key. Events associated with the same key will be published to the same topic partition. And events not associated with any key will be published to topic partitions in rotation. Let's see how you can publish events to topic partitions using the following example. Suppose you have an event source 1, which generates various log entries, and an event source 2, which generates user activity tracking records. Then you can create a Kafka producer to publish log records to log topic partitions, and a user producer to publish user activity events to user topic partitions respectively. When you publish events in producers, you can choose to associate events with a key, for example, an application name or a user ID. Similar to the Kafka topic CLI, Kafka provides the Kafka producer CLI for users to manage producers. The most important aspect is starting a producer to write or publish events to a topic. Here, you start a producer and point it to the log topic. Then you can type some messages in the console to start publishing events. For example, log 1, log 2, and log 3. You can provide keys to events to make sure that the events with the same key will go to the same partition. Here you are starting a producer to user topic with the parse.key option to be true, and you also specify the key separator to be comma. Then you can write messages as follows. Key user1 value login website. Key user1 value click the top item. And key user1 value logout website. Accordingly, all events about user1 will be saved in the same partition to facilitate the reading for consumers. Once events are published and properly stored in topic partitions, you can create consumers to read them. Consumers are client applications that can subscribe to topics and read the stored events. Then, event destinations can further read events from Kafka consumers. Consumers read data from topic partitions in the same order as they are published. Consumers also store an offset of each topic partition as the last read position. With the offset, consumers are guaranteed to read events as they occur. A playback is also possible by resetting the offset to 0. This way, the consumer can read all events in the topic partition from the beginning. In Kafka, producers and consumers are fully decoupled. As such, producers don't need to synchronize with consumers. And after events are stored in topics, consumers can have independent schedules to consume them. To read published log and user events from topic partitions, you will need to create log and user consumers and make them subscribe to corresponding topics. Then Kafka will push the events to those subscribed consumers, and then the consumers will further send to event destinations. To start a consumer is also easy, using the Kafka consumer script. Let's read events from the log topic. You just need to run the Kafka console consumer script and specify a Kafka cluster and the topic to subscribe to. Here you can subscribe to and read events from the topic log_topic. Then the started consumer will read only the new events starting from the last partition offset. After those events are consumed, the partition offset for the consumer will also be updated and committed back to Kafka. Very often, a user wants to read all events from the beginning as a playback of all historical events. To do so, you just need to add the From Beginning option. Now you can read all events starting from offset 0. Let's have a look at a more concrete example to help you understand how to build an event streaming pipeline end-to-end. Suppose you want to collect and analyze weather and Twitter event streams so that you can correlate how people talk about extreme weather on Twitter. Here you can use two event sources: IBM Weather API to obtain real-time and forecasted weather data in JSON format, and Twitter API to obtain real-time tweets and mentions, also in JSON format. To receive weather and Twitter JSON data in Kafka, you then create a weather topic and a Twitter topic in a Kafka cluster with some partitions and replications. To publish weather and Twitter JSON data to the two topics, you need to create a weather producer and a Twitter producer. The event's JSON data will be serialized into bytes and saved in Kafka topics. To read events from the two topics, you need to create a weather consumer and a Twitter consumer. The bytes stored in Kafka topics will be deserialized into event JSON data. If you now want to transport the weather and Twitter event JSON data from the consumer to a relational database, you will use a DB writer to parse those JSON files and create database records. And then you can write those records into a database using SQL insert statements. Finally, you can query the database records from the relational database and visualize and analyze them in a dashboard to complete the end-to-end pipeline. In this video, you learned that the core components of Kafka are brokers, the dedicated server to receive, store, process, and distribute events; topics, the containers or databases of events; partitions, divide topics into different brokers; replications, duplicate partitions into different brokers; producers, Kafka client applications to publish events into topics; and consumers, Kafka client applications subscribe to topics and read events from them. You also learned the Kafka Topics CLI manages topics. The Kafka Console Producer CLI manages producers. And finally, the Kafka Console Consumer manages consumers. Welcome to Kafka Streaming Process. After watching this video, you will be able to describe what the Kafka Streams API is and its main benefits, as well as describe what the Kafka Stream Processing topology is. In event streaming, in addition to transporting data, data engineers also need to process data through, for example, data filtering, aggregation, and enhancement. Any applications developed to process streams are called stream processing applications. For stream processing applications based on Kafka, a straightforward way is to implement an ad hoc data processor to read events from one topic, process them, and publish them to another topic. Let's look at an example. You first request raw weather JSON data from a weather API, and you start a weather producer to publish the raw data into a raw weather topic. Then you start a consumer to read the raw weather data from the weather topic. Next, you create an ad hoc data processor to filter the raw weather data to only include extreme weather events, such as very high temperatures. Such a processor could be a simple script file or an application which works with Kafka clients to read and write data from Kafka. Afterwards, the processor sends the processed data to another producer and it gets published to a processed weather topic. And finally, the processed weather data will be consumed by a dedicated consumer and sent to a dashboard for visualization. Such ad hoc processors may become complicated if you have many different topics to be processed. A solution that may solve these challenges is Kafka. It provides the Streams API to facilitate stream processing. Kafka Streams API is a simple client library aiming to facilitate data processing in event streaming pipelines. It processes and analyzes data stored in Kafka topics, thus both the input and output of the Streams API are Kafka topics. Additionally, Kafka Streams API ensures that each record will only be processed once. And finally, it processes only one record at a time. Kafka Streams API is based on a computational graph called a stream processing topology. In this topology, each node is a stream processor, which receives streams from its upstream processor, performs data transformations such as mapping, filtering, formatting, and aggregation, and produces output streams to its downstream stream processors. Thus, the edges of the graph are the I/O streams. There are two special types of processors. On the left, you can see the source processor, which has no upstream processors. A source processor acts like a consumer which consumes streams from Kafka topics and forwards the process streams to its downstream processors. On the right, you can see the sink processor, which has no downstream processors. A sink processor acts like a producer which publishes the received stream to a Kafka topic. Let's redesign the previous weather stream processing application with Kafka Streams API. Suppose you have a raw weather topic and a processed weather topic in Kafka. Now, instead of spending a huge amount of effort developing an ad hoc processor, you could just plug in the Kafka Streams API here. In the Kafka Streams topology, we have three stream processors. The source processor that consumes raw weather streams from the raw weather topic and forwards the weather stream to the stream processor to filter the stream based on high temperature. Then the filtered stream will be forwarded to the sink processor, which then publishes the output to the processed weather topic. Concluding, this is a much simpler design than an ad hoc data processor, especially if you have many different topics to be processed. In this video, you learned that the Kafka Streams API is a simple client library to help data engineers with data processing in event streaming pipelines. A stream processor receives, transforms, and forwards the streams. Kafka Streams API is based on a computational graph called a stream processing topology. And in the topology, each node is a stream processor, while edges are the I/O streams. And finally, in this topology, we find two special types of processors, the source processor and the sink processor.